Hello Year 12, it's Mr. Robertson again. I'm really pleased to be with you in some small way. I hope you enjoyed the video yesterday, another short one for you today. But before we get to that, can I just say a huge well done. You guys have been fantastic. Mrs. Graff is telling me every day about your brilliant effort, how much fun she's having in class, how hard you're working. Not all of you, some of you could work a little harder, but most of you. And I know that those who are having difficulty are really trying to find a way to get through the concepts and to improve on your ability to apply the techniques. I'm really pleased. I'm so looking forward to coming to work with you. The biggest message I get from Mrs. Graff every day is that you're going to love working with these guys. So I'm excited. I hope that you are, and just keep up the great work. I'm really, really impressed. You guys have absolutely nailed it. I'm proud of what you've done. I'm proud of your approach to the course, and I know you're going to be successful. So it's going to take some hard work and some continued effort. Now, I know that I'm not there with you. I've not been able to make a little welcome video yet. Unfortunately, it's tricky to be up and about at the right time to do that. So I thought what I'd do is share with you a little video of the last time I was teaching in China, a little funny video that I quite like, but it might give you a little bit of idea of the fun that we might have in the classroom. I know that you guys enjoyed having a laugh. So here's a short video just to show you a little bit about me. Let's see if it works. Yeah, I'm pretty sure it's going. Okay, so this is Mr. Robertson's maths class on Wednesday the 15th. Okay. I think we'll do that again. Yes, I will save that. Don't worry, I will save that. Not sure what happened there. Jerry, you okay? Okay, let's try again. So I hope you enjoyed that. I hope that we can have some fun over the course of the session too. And I'm really looking forward to seeing you all very soon. So let's look at today's lesson. We're going to look at how to differentiate ln x. So I'm going to do that first of all by looking at a package called GeoGebra. There are lots of great animations that go through quite a few of the ideas in mathematics. So this one might help us with ln x. So here we go. Okay, let's have a look at how we might find the derivative of ln x by using the idea of gradient and the gradient of the tangent to that curve. So if we just show you ln x here. Now, logarithmic functions have some properties in terms of the graphs. We're not really talking about that today. I know there's lots of things that you're maybe not sure about. I'm really sorry that we're having to do that at the moment, but let's just focus on the ideas that we're using for differentiation just now. And I promise we can go into some detail on these functions. In fact, we will go back and look at these functions in more detail this session. But basically, it's got this basic shape here. It's going to go through the point 1, 0. It's only valid for x is greater than 0. So x equals 0, there is no value. In fact, the y-axis here is what we call an asymptote to the logarithmic function. And you can't put any negative values into ln x. You try that with a calculator. If you try ln of -2, then you'll have a problem. And we can see that it's got this property. It's coming from negative infinity all the way up. It's going all the way around, and then it's sort of constantly climbing, but very slowly. So this is the graph of y equals ln x, or log to the base e of x. And again, Mrs. Graff can stop the video and talk to you about this if needed. So there's the function. We want to try and find the gradient at a certain point. And we do that by thinking about the gradient of the tangent. So really we're thinking about as we move along the curve, what's happening to the gradient at each point? Well, it's the same as the gradient of the tangent that we could draw to the curve. And we find the gradient of the tangent, of course, by just doing a quick y2 minus y1 over x2 minus x1 calculation. Change in the vertical height divided by the change in the horizontal. So we can find the gradient of this tangent at all these points. So what's happening to the gradient of that blue line? Well, if we're down here, we can see actually that it's coming from a very high gradient. In fact, If we keep trying to move down there, then we're getting a line which is slowly getting steeper and steeper and steeper. But if we go the other way, then that gradient is coming down, it's getting smaller, it's getting smaller. It's never going to quite go to zero, and it's never going to be negative. It is constantly getting smaller and smaller and smaller, so it might be 1/2, 1/3, 1/4. So that gradient has changed in a very predictable way here. And in fact, to work out how to find the gradient, we need to think about how to plot those values. And if we do that, we see that actually f dash x is just 1 over x. So for example, if we move to the point where x equals 4, so here, the gradient of that blue line is actually 1 over 4, which would be 0.2483. And as we keep moving along the x-axis, the gradient is constantly going to be 1 over the value of the x-coordinate. So actually for y equals ln x, the derivative is 1 over x. But let me show you how to do that with some algebra. Actually, just before we do that, let's look at some more animation from GeoGebra. So this particular teacher has put together something where we can look at the graph of the derivative being drawn as we move along the function. So again, we're just calculating the gradient of the tangent at a particular point on the curve. As we do that, we see that the graph that we trace out for f dash x is actually just y equals 1 over x. It's the reciprocal function. So that's what's happening here. Y equals f dash x is really just y equals 1 over x. Okay, let's look at the algebra involved in differentiating logarithmic functions. I should say actually logarithms were invented by a Scotsman, John Napier, so do check that out. But he was looking at all sorts of problems, and he came up with a great way to perform calculations. But the basic idea is we look at 10 squared equals 100, and we know that that is an exponential expression. So we have a base, in this case 10, and the index is 2, but we also call that the power or the exponent. So this is an exponential relationship. And the logarithmic version of that was invented or discovered was that log to the base 10 of 100 equals 2. So the base here is also the 10. The base stays the same, but it's another way to look at that. It's a sort of inverse function approach. So we could say that 2 cubed equals 8 is an exponential expression. The logarithmic version would be, well, log to the base 2 of 8 equals 3. So we can have any base for these logarithms within reason. There are some constraints. But we really are saying here that if there's an exponential relationship, then there is an inverse to that. And this inverse here is the logarithmic function. So 9 to the power of half equals 3. We could say that log to the base 9 of 3 equals 1/2. So some of you might know this already, some of you might not. Don't worry too much about that right now. What we're really saying here is that if there's an exponential function, let's say y equals, now we know there's a very special exponential function e to the x. If we've got y equals e to the x, then the inverse function is a logarithmic function, and that would be y equals log to the base e of x. So e is this special base that we can use. It has a lot of interesting properties. It occurs naturally. But in today's example, we're going to use the base e, and we actually call that, we give it a very special name. It's called the natural logarithm because it occurs in nature. So that's called ln x. If we look quickly at the graphs of these two functions, again, Mrs. Graph has probably shown you this a few times already, but the exponential function and logarithmic function are the inverse of each other. So that means if we draw the line y equals x, then they will be a mirror image of each other in that line. The exponential function looks like this, and it goes through 0, 1, because e to the power 0 would be 1. Anything to the power 0 is always 1. So the logarithmic function would look something like this. And if e to the x goes through 0, 1, then this will go through 1, 0. So that's the function in blue that we're trying to find the derivative of, y equals ln x. And that's going to be the challenge today, is to try and find the derivative of this function, ln x. And we're going to do that in a very particular way. So I'm going to show you that now. Okay, let's have a look then at y equals ln x. In order to differentiate this, we're going to rewrite that as y equals log to the base e of x, which of course it is. So we write that as y equals log to the base e of x, and then we're going to change that to an exponential relationship. So you remember I said we could do that in the last slide. So all we're doing here is saying that that means that x equals e to the power of y. Now, we can differentiate this if we differentiate with respect to x. So if you like, x and y have changed places here. So we can find what we call dx by dy, the derivative of this expression with respect to y. Now, Mrs. Graf might want to pause at some point here if you want to ask questions about what we're doing here, but I can tell you that we're going to look at this in the later part of this course, so don't worry about this technique. You don't need to do this right now. But we should see that dx dy is just going to be e to the y. Now, how do we get from there to dy by dx? We've got this the wrong way around. Well, we could think about the chain rule here. We know that it is true, because of ideas connected to the chain rule, that if we've got dy by dx times by dx by dy, then that just equals 1. Now, there's kind of a cancelling idea here. It seems like we're just cancelling dy and dx. And sometimes we think about it that way. If you think about the chain rule, dy by du by dx. So we could think about cancelling here, dy by dy on both sides and dx on both sides, but that's not quite what's going on. What we're saying here is that dy by dx would be the reciprocal of dx dy. It would be 1 over dx dy. So what I'm saying here, year 12, is that we can flip the right-hand side if we flip the left-hand side. So dy by dx becomes 1 over e to the y, which is 1 over, well, what is e to the y? We said that that is just equal to x. So yes, the derivative is 1 over x. And we saw that graphically, I hope. Here's how we might prove that algebraically. But I know that we don't have a full understanding of some of these ideas yet, so don't worry. What you need to know, and it's in the textbook, is if f of x equals ln x, then f dashed x will equal 1 over x. And that's what we're going to work with in some of the questions we're going to try today. But we have to ask this question again that we keep asking: what happens if it's going to be ln of a function of x? So we've got to bring the chain rule in here. Okay, so we want to think about what happens if we have to differentiate y equals ln and it's a function of x. So we've had this question occur in yesterday's lesson. We know that we can use the chain rule here. We just need to look at some examples of what we need to do. So hopefully these examples will help you, and you'll try some questions today and you'll have a better idea of the technique. So let's say that y equals ln of 7x. How do we differentiate that? What's the answer going to be? Is it just 1 over 7x? Well, we have to be careful. We have to think about the chain rule. So let's do that in full. Remember, we don't want to do this in full each time, but let's do it here. So let u equal 7x means that y equals ln of u. We differentiate each of these. So du by dx is just 7. And dy by du, well, the derivative of ln u is 1 over u. And that means that the derivative dy by dx is the product of these two. So it'll be 7 times 1 over u, or 7 over u. We swap u for what it actually is, which is 7x, and something interesting happens. The answer is still 1 over x. So that catches some students out. Be very careful. To summarize that, really, if the function is just a multiple of x, so a constant, like k times x, so ln of kx, where k is some constant, then dy by dx is still just going to be 1 over x. Now that's a case that only applies for that particular situation, where this is a constant. Let's look at what happens if it's a more complicated function. So let me remove some of this. Again, you don't need to copy this just now, though we can pause the video if you want to write some of this down. I'll let you decide, Mrs. Graf, if they need to do that. But let's get rid of some of this just now and look at something more complicated. So not 7x, what about if we look at 7x squared? Now here we probably would put a bracket around the 7x squared. I haven't done it at the moment, but really we should. So we should really put a bracket around 7x squared because we're taking the natural logarithm of that function. So here, if we differentiate using the chain rule, we differentiate the function, so we get 14x, and then we times it by the derivative of ln of 7x squared, which is 1 over 7x squared. And now when we multiply, we can cancel. 14 over 7 is 2, and x over x squared is just 1 over x, so the answer is 2 over x. Where did that 2 come from? I think you should be able to see where that 2 came from. And here, if you look at something even more tricky, ln of 4x cubed plus 1. Well, all we need to do using the chain rule that we're becoming better and better at is to differentiate the term inside the bracket. So that will be 3 times 4 is 12, x squared. Derivative of 1 is just 0, so it's 12x squared, and over the denominator. Over the term inside the bracket, so 4x cubed plus 1. So what's happening here is that to find the derivative, we actually end up with the derivative of the function inside the bracket, f dash x, divided by f of x. So actually there's a really straightforward pattern, and Mrs. Graf will point that out to you today. Now, in order to be successful in the exercise, there are some other things you need to know, and those are the 3 important logarithmic laws, log laws, which you may have seen before. You should have studied these in IGCSE FP, but I know that we won't all have. So you'll need a bit of help with these. Mrs. Graf will be on hand, I'm sure, but here they are. So we have 3 laws that we can use. If we have the logarithm, or the natural log of a product, a times b, then we can separate that into a sum, log of a plus log of b. Ln of a product equals the sum of the 2 individual logarithms. If we have the logarithm of a quotient, so ln of a over b, then that's ln of a minus ln b. And the third one, which is a little tricky, if we have ln of something raised to a power, so a to the power n, we can bring that power down and multiply by log of a, so it's n times log of a. So Miss Graf might want to talk to you about these, or we can just wait till you get to questions that involve those. I'll do a very quick example. It's the one that's in the textbook, and let me go through this a little carefully. So page 455 from the textbook that we have been using occasionally, y equals ln of, and we're given here x multiplied by e to the negative x. So how on earth do we differentiate this? Well, in the bracket is a product. Now that doesn't mean that we're trying to use the product rule. That's not what we're going to do here. There's an easier way. So what we're going to do is see that we can separate that using the first law as ln of x plus ln of e to the negative x. Now ln of x we leave alone for the moment. How do we write ln of e to the negative x? Well, that's log law 3, because there's a power there that can be brought down to the front. So the negative x can be brought down to the front, and we're left with ln of e. And finally, we haven't done any differentiation yet. Finally, we see that that's actually just equal to ln of x minus x, because ln e just equals 1. Log to the base e of e is just 1. So you see how important it is that we write down each and every step. Now we're going to differentiate, and that's quite easy. Derivative of ln x is 1 over x, and the derivative of negative x is negative 1. That's not an easy question, but it's much easier if we take our steps carefully and we write down clearly what we're doing, one line at a time. So let's look at what I want you to do or to try for this final lesson. Okay, so here's the exercise I want you to try today. My apologies for such a long video this afternoon. I hope that you're feeling okay and you're up for giving this a try. I want you to try question 1 and question 3. Mrs. Graff can pause these on the board, or you can do them from the digital copy of this exercise. You will need some help. I think it might be something to take off into the weekend for some homework, but I'll let Mrs. Graff decide. Good luck, Year 12. I hope you have success and you get all or as many as you can correct. Have a nice weekend.